Okay, so I guess the plan for today is to talk a bit more about bandits, which we started last week. So I mentioned a few kind of improvements we can make to a learning algorithm, but that's it's sort of an endless topic, so we'll just try to keep it brief, and then talk a bit about like a lower bound on bandit algorithms to see how close we get to being optimal, and then try to do like a quick overview of learning and optimization for MDPs and POMDPs, which will be in a very high level, just to give you a sense of what's going on there. I guess what we did last time, or I guess first of all, just a high level comment is that I guess bandits are kind of special in the sense that it's sort of a pretty narrow setup, but a lot of the ideas are actually like that come up when looking at the simple case of bandits are actually like fairly general ideas. So I think in that way, it's sort of a good playground or toy example. But I guess even calling it a toy example, I think is a bit misleading because it really does contain a lot of the interesting bits of learning. So that's just, I guess, the reason we're spending a decent amount of time on bandits, because they're fairly simple setup, but a lot of yeah, contain a lot of the substance already. Yeah, so last week we looked at the explored and commit algorithm etc, and then already towards the end of the class we mentioned a few sort of drawbacks of this algorithm. So we looked at we analyzed to some extent the case when we explore each arm m times, where m was roughly something like, I think we did 4 over delta squared log of t delta squared over 4. I guess the exact form doesn't matter, just there's some main issues with this. One issue was just that it's not any time, so it depends on the time horizon. And then another issue was that, maybe a bigger issue was that it depends on the suboptimality gap delta. And then another thing was that we only really did this analysis for 2 arms. And I guess the fourth thing we might mention is that we basically decided how long to explore each arm ahead of time, and we did not like look at the data, the outcome of those arms at all for that decision. So sort of let's say we ignored a lot of data by choosing ahead. So these are just a few kind of things that could be said are problems with the algorithm that we presented. But I guess the main benefit of it was just it's a very simple algorithm, and it was very conducive to analyzing because of its simplicity. But we can look at a few ways in which we can kind of try to improve on these shortcomings. So for the dependence on the time horizon, I guess if people did homework 3, question 3, that was sort of one approach one can take to turning it into an anytime algorithm, which is to kind of split the time into these epochs or into these like larger and larger chunks, and then run different time horizons for those bits. A different approach we can do here is to use a relative of etc, which is it's called the Epsilon-greedy algorithm. So in explored and commit, we had like an initial phase where we explored and we tried each term a certain number of times. And then afterwards we turned into exploit and we just committed to the best term. In Epsilon-greedy, we do something similar, except we kind of spread out the exploration kind of across time. So basically, the way this works is that with probability epsilon, we choose a uniformly random arm. So like each turn we flip a coin, like with probability epsilon. If the coin comes out heads, then we choose a uniform arm. I guess we flip a second coin to choose an arm. If it came out tails, so there's the remaining 1 minus epsilon case. Otherwise, choose the best so far based on the, I guess, best based on the empirical average. So technically this should be called 1 minus epsilon greedy algorithm, because it's with a small probability we're not greedy, and with a high probability we're greedy. And then I guess one advantage of this is that we don't have to do all the exploration at the beginning, so we can actually we can tune epsilon and we can allow it to vary over time to get an anytime algorithm. So basically we can explore more in the beginning, and later as time goes on we just explore with a lower and lower probability. So we'd in general like expect epsilon to go to 0 as time goes on. And yeah, so here I don't want to go into detail, but there's in the notes I wrote down some more precise statements of what you can choose epsilon t to be, and what kind of bounds you can get from it. Right. Any questions about the idea of Epsilon-greedy algorithm?
I guess just a quick one. This solves all the problems you listed.
No. I think it solves, well, in this naive form where we're just allowed to vary epsilon over time. It sort of addresses the first problem reasonably well, but yeah, in general, I guess at first we don't know, like probably a good choice of epsilon would still depend on delta, so there we would need to do something else too. I guess it does it does maybe address number 3 somewhat. I think that maybe the Epsilon-greedy. It's fairly easy to generalize to more arms. I mean, okay, I guess it would still have the same problem that export and commit is also easy to write down for the arms, but to figure out what the right expiration time is harder. So it probably have the same issue. So yeah, I would say the answer is no. It doesn't solve all the problems. It solves the first problem maybe reasonably well. I guess that's why I wrote the 1 here. And then yeah, if you wanted to, I guess, have a better solution, and this would address maybe 2 to 4. I guess actually 1 to 4 pretty well too. So this is a more sophisticated algorithm. Well, first, okay, maybe I should say number 2, we're going to address some homework for question 1, I think, is going to be talking about how to turn the export and commit algorithm into something that works for any, or which doesn't depend on the knowledge of the suboptimality gap delta. So that's one possible approach. But I guess for the lecture, I just wanted to mention another approach, which is a fairly different idea for the algorithm. It's an algorithm called UCB, which stands for upper confidence bound. And the kind of underlying principle of this algorithm is what might be called optimism. So on a high level, the way it works is that at each time step, we compute, let's say, some 1 minus delta confidence intervals. Where we'd have to, again, choose delta carefully. So these are confidence intervals for the means of each arm. So let's say there are 3 arms. Arm 0, arm 1, arm 2. And then based on the data we have so far, we can compute some let's say 90% confidence intervals if this is the for the mean of each arm. So let's say something like this. Like this. So I guess the width of this confidence interval is going to depend on how many times we pull the arms, as well as the rewards that we observe. And then this principle of optimism is just basically saying we pick the one with the optimistically best, possibly best output, which in this case would be A1, because the possible highest mean this can have based on our confidence interval is the highest here out of the 3 arms. And then I guess on a high level, basically, in this case, we would choose A1, but it also has the widest confidence interval, which means we're kind of uncertain about it. But as we're optimistically picking it, we're also like pulling that arm more and more, which means that the confidence interval will decrease. So if we were pretty wrong about our optimism, then soon we'll find out, because maybe the confidence interval will go eventually will go lower. Maybe it would over time it would shrink to this confidence interval, and then afterwards we would pick that one which is optimistically better, and then as we're choosing that one again, that confidence interval will shrink as well. So that's sort of the high level idea. And again, I wrote down more detail in the notes if you want to see how it's defined formally. Are there any questions about the high level?
Is delta decreasing with t, or is it constant?
Right, that's a good question. I guess it's similar to before, where if we wanted a non-anytime algorithm, we can just fix delta based on the time horizon. But of course, if we want an anytime algorithm, then we cannot do that, because any kind of fixed finite delta eventually will be kind of too big. It would lock us into a kind of bad situation. So if you want an anytime algorithm, we would have so if you wanted a anytime algorithm, we would want to pick a delta that depends on t, and
why is it so? Why is it so? Don't you still get the intervals to shrink?
You still get the intervals to shrink somewhat.
I think you have a counterexample that shows that you cannot learn if delta is constant, because let's say this non-optimal arm is constant, then its interval will always shrink. And then, because you have bad luck, you tried the optimal arm and you got a small interval below it, less good than it. Then you will always continue doing the non-optimal arm with the constant reward, and you don't get out of this hole.
Right. Yeah, that is a good point. So basically,
can you repeat the counterexample? Maybe draw. I'm not sure.
Yeah, so let's say there are just two arms, A1 and A2. And then let's say for A1 or for A2, we just have a constant return, so the confidence interval will keep shrinking here. But let's say for A1 we got unlucky and we had a few like very low samples, so we get a confidence interval like this, like way kind of significantly below this one. But it turns out the true mean is better than, so actually A1 is better than A2. We just got unlucky in the beginning, but then because we got unlucky, if we keep delta constant, then the confidence interval for A1 will remain what it is, and we just keep pulling A2 forever, and no matter how much this A2 interval shrinks, it never shrinks below to where A1 was. So yeah, in that way, if we keep delta constant, we can get unlucky in the beginning and just lock into a bad situation, which is kind of a similar thing that happens to if you did question 2 on the last homework 3, the follow the leader, where you just pull whichever arm was best so far. In that case too, if you're kind of unlucky in the beginning, then you can lock into a bad situation. So it's a similar sort of problem. Then you don't want any bad luck in the beginning to lock you in forever. Does that make sense?
Yeah, that makes sense.
Yeah.
For all these examples, is the only way to know their properties is to like sit down and do the calculations? Or is there some intuitive insight that says, yeah, UCB is obviously better than ETC?
I guess there's not an obvious thing. I guess one thing that maybe could be mentioned is just that UCB is kind of using the data to make decisions,
Yep.
while ETC was not using any of the data. And you could upgrade ETC where you explore in the beginning and your exploration time is allowed to depend on the outcomes of the rewards. And that way you could also improve ETC. So I guess basically all of these algorithms you can kind of keep refining with various ideas, and you can get like various improvements sort of indefinitely.
Is there like a best one?
I would say not really, like because the more sophisticated the algorithm, the harder it gets to analyze, and it's also like a little like if you're in a more special case where you, let's say, restrict to just Gaussian bandits or just Bernoulli bandits instead of all sub-Gaussian ones, then maybe you can exploit certain special properties of those distributions, and then have like a specialized algorithm which is better in that narrow case. So there's a trade-off between like how general the algorithm is and how well it works in a specific case. So yeah, I think it's hard to say there would be a best one in any meaningful sense.
Mm-hmm.
Okay. So yeah, as I said, these are just, I wanted to mention these sort of algorithms just so you know about them, and I wrote a bit more detail in the notes. But yeah, I think what would be interesting to see is to actually derive or sketch how to derive a lower bound for bandits. So that will be our next topic today, is to try to get a lower bound. So this would be something that says for any algorithm, any learning algorithm, it cannot do better on a certain class of bandits than a certain bound. So it would be sort of something of the form, for all learning algorithm pi, there exists an eta, a bandit in whatever hypothesis class of bandits we're looking at, such that the regret of t up to time t of pi with regards to eta is bigger or equal to something. And then I guess the thing we'll sketch a proof for today is that for if we take H to be, let's say, one sub-Gaussian bandits, and then maybe you can modify this sort of argument for other classes, then we can find a bound which is of the form C times square root of the number of arms minus 1 over T for some universal constant C. So basically this is saying this 1 over square root of T bound that we got for ETC or any of the other algorithms, it cannot really be improved, at least as far as the exponent of T goes. And then this constant C is going to be probably the thing we derived today is going to be fairly small compared to the upper bound, but that's another thing that one can try to sort of refine and get the two bounds closer to each other. But this is going to be our goal for today, to show something like this. So the idea behind getting such a lower bound is to find two bandits, eta 1 and eta 2, which have two properties. One is eta 1 and eta 2 are kind of hard for pi to distinguish. And we'll be a little more precise about this. And the other is that the regrets for eta 1 and eta 2 cannot both be very small. And I guess these two properties are sort of creating opposite pressures to each other, where if eta 1 and eta 2 are very similar to each other, then you would expect they would have quite similar regrets as well. So we're going to have to kind of find a balance between these two properties that creates enough of a gap between them to have a lower bound. Does this high-level plan make some sense? So let's go into like let's call it proof sketch. I won't be proving every detail, but hopefully give you an outline of the proof that could be filled in if needed. So for the sake of this proof, we're gonna, I guess at the last time I said we can always just think about Bernoulli bandits, but today we're gonna actually, for the sake of this proof, we're gonna look at Gaussian bandits. But the main reason for that is just they're easier to calculate a certain quantity with. So it's not really essential. You can do a similar construction with the Bernoulli bandits as well. So okay, let's look at the first bandit. Let's have this vector of means, which is first of all, okay, let's fix pi and t. So we're working for a fixed policy and a fixed time. And then we look at a bandit which has mean delta for the arm 0 and then mean 0 for every other arm. So this is a vector in I guess 0, 1 to the a. So it just specifies the means for each arm, and we take the bandit itself, eta 1, to be normally distributed with these means and variance 1. And then, so this delta is something TBD.
All the other means are 0?
All the other means are 0, yes. 0, 0. So we have the 0th arm is going to be the optimal one for this environment with mean and delta, and every other arm has mean 0, so they're all equally bad. And yeah, so this delta we're gonna choose later. For now, we just call it delta. Okay, so if we play against this bandit mu1 using our policy pi, there's gonna be one of the suboptimal arms that we pull the least number of times, the fewest times. So let's call that L. So this is the L in A be the least pulled arm, I guess suboptimal arm by pi, which we can write as L is, I guess, equal argmax.
You mean least pulled for the entire T rounds or so far?
For the entire T rounds.
Okay.
So this is going to be the argmax of the expected value under the distribution of the interaction of eta 1 with pi of the counts of each arms up to time t. So this C of A is the just count how many times we put
Shouldn't
arm
it
A.
be argmin?
Argument, yeah, I think so. Argument. Yeah, the least full line. Thanks. So in particular, actually, so I want this specifically to be the least pooled suboptimal arm. So, which I guess might not matter that much, but let's say for precision, let's say this is a non-zero arm. So given this, we actually have that L has to be always less equal than T over the number of arms minus 1, because there are A minus 1 suboptimal arms. So the least pulled one has to be the fraction of times it's pulled is 1 over A minus 1.
Should that be CL or is that L?
Well, this is the argmin over A of CA. Sorry. I do mean, what do I mean? I mean CL, yeah. CL, or yeah. I guess the expected value of under eta 1 pi of CL of T. Yeah, thanks. Yeah, so the expected number of times it's pulled is going to be less or equal than T over A minus 1. Okay, does this make sense so far?
Yes.
So now, given this, we can choose a mu2, which is going to be very similar to mu1. You will have delta for the 0th mean, 0 everywhere else, except at the lth position, you will have 2 delta. So this is the lth mean. And then we'll have the associated eta 2, which is the normal Gaussian bandit with the mean mu2 and variance 1. So for eta 2, the optimal arm is now actually the lth one, but every other arm looks the same as for eta 1. Okay, so I guess the goal will be, as I said in the beginning, with these two properties, we're going to try to choose delta to be small enough that eta 1 and eta 2 are pretty similar. So pi behaves kind of similarly, but large enough so that the fact that the optimal arm is different for the two actually matters for the regret. So, okay, let's see. We can say that the regret up to time t of pi against eta 1. So for eta 1, the optimal arm is the 0th arm. And anytime we pull something that's not the 0th arm, we incur unexpected regret of delta. So we can put a bound on this, that this is bigger or equal than the probability, and I write P of 1 to stand for short for P of eta 1 paired with pi. So this is P1, and let's look at the case where the count of arm 0 up to time t is bigger or equal to the regret is, for the regret we want is lesser or equal than t over 2. So this is the case where we pull the optimal arm less than half of the time. In that case, for half of the time, we suffer delta regret. So we get a delta over 2. And this is average regret. So the total regret would be t times this, but divide by that. Does this inequality make sense?
Can you repeat the explanation?
So here we have the probability of the event that we pull the 0th arm fewer than half of the time, or fewer or equal than half of the time. And each time we do that, we suffer a regret of delta.
Okay.
So the average regret we get is at least delta over 2 times this probability. And then this is where the way we picked eta 2 comes in, because now the regret for eta 2, here every time we pull arm 0, we're accumulating regret. So here we get that probability under eta 2 that C of t is bigger than t over 2 times delta 2, delta over 2. So here, each time we are not pulling the nth arm, which is included in the case where we pull the 0th arm, we get a regret of delta. So similarly, if we pull the 0th arm at least half of the time, then each of those times we incur a regret of delta. So we get these two bounds. Does this one make sense as well? Right. So now we can say that the sum of these two regrets this is bigger or equal than delta over 2 times, and then we have this probability under bandit 1, and then maybe we can call this event A, and this one is exactly the complement of that event, so we call it A complement. So we have a probability of some event A under P1 and the probability under bandit 1 of the complement of that same event. And then here, so here's where the thing comes in, where if eta 1 and eta 2 are similar enough to each other, like if P1 and P2 were the same, then the sum of these two probabilities would be 1 because they're probabilities of complementary events. But they're not the same probabilities, but still we can actually bound this from below by 1/2 times e to the minus, and there's this quantity called the KL divergence, or relative entropy of one distribution relative to the other. So this bound is called what is it called? Bertagnol Huber inequality. Okay, so this we're just going to use out of the box right now, but if you're interested, you can look up on Wikipedia, for example, what this is. Okay, so we have a lower bound here. Now we just need to work out what this KL divergence is. Yeah. Any questions about this aside from this black box inequality that I'm using? Okay, so assuming this lower bound, we just need to work out this KL divergence. So I guess this is the KL divergence between the distributions which are pairing eta 1 with pi, and I guess just up to time t, and pairing eta 2 with pi up to time t. And it turns out this is something, again, I'll skip, but this is a lemma we would need to prove. So it turns out this is equal to, in general, to the sum of the expected number of times is the sum over each arm. The expected number of times under environment 1 of the count of arm A up to time t times the KL divergence of the distribution of that specific arm. Here's that right, eta 1A, eta 2A. So this basically says, okay, we have the distribution for each arm, which has a certain relative entropy for the two bandits, and then for the entire destiny distributions, in order to get the KL divergence, we need to sum these up and multiply them by the number of times we pull that specific arm, which is maybe intuitive because the more you pull the arm, the more the divergence adds up for that arm. And then in our special case, the only KL divergence that's going to be non-zero is the one for the Lth arm, because that's the only place where the two distributions differ. So this is going to be equal to the expected number of times under bandit 1 that the 0th arm is pulled, or the Lth arm is pulled, times the KL divergence between eta 1 for that arm, which was just mean 0, variance 1, normal distribution, and then the other arm had a mean 2 delta and variance 1. Right. Maybe I'll pause this for a minute for people to ask questions or digest.
Why is it again that this sum simplifies in that way to just this one arm?
Right, so I guess we have the KL divergence for each of the arms, but the two distributions that we picked, one was this one, delta 0, 0, 0, 0, and the other one was almost the same except for the Lth arm. So the distribution for each arm is the same except at the Lth place, which means that
don't we also need to add the entropy of each of all the normal around zeros, like the DKL the divergence of a distribution with itself, if I remember correctly, it's the entropy, right?
I think for the KL divergence, that should be 0. For if you put, so maybe that's one way to say, is it dKL of a distribution with itself is 0.
I have another question. In week 2, when we defined utilities, we said that they take a value between 0 and 1. But now, if the bandits have a normal distribution, doesn't that mean that it can be outside of that interval?
Yeah, so we're kind of, we put that assumption aside for now. But as I said, you could work this argument through for a Bernoulli bandit, for example, too, in which would satisfy that assumption. It would just be, I guess, actually the only place you would be doing this calculation would be a little harder, because for normal distributions, it's fairly easy to compute the KL divergence. But yeah, so that assumption, I think, yeah, I mean, it's an assumption, so you can either take it or not. But now we're just, we're not assuming that, yeah, you're right.
There's some asymmetry here because we're using the expectation of the counts according to 8 or 1.
Yes,
Is
yeah,
that
so
quite important in this?
yeah, so I think the KL divergence itself is asymmetric, so you,
Yep.
yeah.
Oh, I see. If you swapped 8 or 1 and 8 or 2 in DKL.
Yeah. Yes, yeah, I think you'd probably get maybe the same thing. But yeah, you're right. It is asymmetrical. But I guess, I mean, that's intentional too, because we picked L in a way that was dependent on the first bandit in particular. The thing we're gonna use is that this one we banded above by what was it, T over A minus 1. So yeah, that asymmetry is there, and it's, I guess it's useful in our case. Okay.
So going back to the Bretagnol-Huber inequality, what that's saying is that if P1 and P2 are the same, for example, if P1 and P2 are the same, then probability of A plus the probability of A complement is going to be greater than or equal to a half, right?
Right. So it's actually not the strongest inequality you can get. There are improvements on this, but it's good enough for our purposes. Yeah.
And then as the KL divergence between these distributions increases, this lower bound is going to decrease, actually. So it's going to become a weaker bound.
Exactly. Yeah.
So it's basically saying, okay, these two probability distributions, as they become more similar, probability of A plus A complement in these two different distributions is better and better bounded below, basically.
Exactly.
Cool. Very interesting. Cool.
Okay, as I mentioned, the main reason we're doing normal distributions here instead of Bernoulli, just so that this KL divergence is pretty easy to compute, and it comes out to be, I guess, the difference in means, which is 2 delta squared over 2. So overall, I guess summarizing this, we get that sum of the 2 regrets this is bigger or equal than here we had 2 over A minus 1. Here we have a 2 delta squared over 2 Uh, and I guess this is yeah, this is in the exponent, so maybe okay, maybe I'll save this for a second, and we can choose delta now, and then that will simplify the bound instead of writing this out. So now, okay, you're ready to choose delta. So here, I guess this product is the product of these two things is t delta squared over 2t delta squared over a minus 1. So we're going to choose delta to be something that matches this. So we're going to choose it to be square root of a minus 1 over 4t. I guess you can tune these parameters, but this is a reasonable choice. So with this choice, we actually get that what this is just equal to 1/2 for that choice of delta. Right, because if we square this, the t and the a minus square cancel out, and we're just left with 1/2. And so what we get for the sum of regrets, which was right, see what is. So if we go back to here, we got a bound on the sum of regrets, which was delta over 2 times 1/2 times e to the KR divergence. So that should give us delta over 4 times e to the minus 1/2, which this choice of delta is equal to some little c times square root of a minus 1 over t, which is what I promised in the beginning. Or, well, 1 over 8 times square root of e. And then based on this, we can say that the maximum of the two regrets the maximum is bigger or equal than 1/2 times the sum of them. So we actually get 1 over 16 square root of e times square root of a minus 1 over t. So this is our lower bound that we get in this case. All right. So that actually took up most of our time. So I won't have time to go into MDPs, unfortunately. But there's one simple question on the homework on MDPs, which is, or actually, it's not that, the question is not that simple, but the definitions you need for it is fairly simple, and I included in the notes, so you can check the definition in order to do the homework. Yeah, so any questions about this lower bound? it took a bit of work to establish it, and we kind of skipped over a few details, but hopefully the kind of high level ideas there. And we get to see that the shape of this lower band is somewhat similar to the upper bands we get. Yeah, so yeah, we can stop here for today. Feel free to leave, and as usual, I'll stay around for 10 minutes. I can either talk a bit about MDPs, or if people want to ask some other questions, we can talk about those as well.
MDPs sounds good. I don't know.
Okay, so I got started on MDPs, and if people think of other questions, let me know. So we saw the definition of an MDP in particular. I guess we defined a POMDP in general, and then we said the MDP, in an MDP, the state is observed. So we can identify the set of states with the set of observations. And then we have a transition kernel for each state, and each action, it tells us what the distribution of the next state is. And we have a, let's say, an initial state in delta S. And then I guess the main thing about MDPs, says like kind of a motto that you can try to make precise, is that bandits you can think of as MDPs with a single state, where there's like basically no states, or just one state, and so the reward only depends on the action that you take. But in an MDP, we have states, so which basically translates to needing to do long-term planning. So it requires some long-term planning. I guess to give you like a rough idea is that, let's say we're in state A, and then we have two options, action A or action B. Action A goes to state B, where we get a reward of 1. I'll put this in the triangle. And let's say in state C, where we end up, we get a reward of 0. So if we kind of myopically, action A seems to be better than action B. But let's say down the line from action C, if we take action A, for example, we go to an action D. And let's say this state has a reward of 100. Again, putting aside the assumption of the reward being in 0 and 1, just for the sake of this example. Well, let's say for B, if we continue, then we end up in a state which is kind of bad again. And you can, let's say this go back to A or something. Maybe B stays here. You can complete this to something where all of the actions make sense. But the point here is that even if the rewards are deterministic, and action A is myopically has better reward starting from state A, in the long run, taking action B and then A is better because we find a state with much higher reward. So that's the kind of thing that happens in MDPs, that you need some sort of long-term planning in order to perform well. So in particular, we see that a sort of greedy policy with regards to the reward doesn't do well for an MDP. But it turns out this can be shown that for each MDP, there's a value function which will depend on the rewards, and it will depend on the transition kernel, on states, such that any optimal policy is greedy with respect to the value. And this also implies that there exists a deterministic memoryless, which is something like a stationary optimal policy. And I guess the thing to note is that this value function it satisfies what's called Bellman's equation. Which basically is sort of an optimality equation for the value function. So basically, even though if you try to be greedy with respect to the reward, it doesn't work. But it's possible to compute a value function, and being greedy with respect to the value function is actually it works in the case of MDPs. So that's an interesting result. And actually having this Bellman function, Bellman's equation, it also allows us to compute the value function pretty efficiently. And actually using all of these, so this is just a kind of control. So this is for the known MDP, and then for the learning, we have a theorem that says there is a polytime learning algorithm pi, and we could take this to be actually a relative of upper confidence bounds, such that the regret for time t for this learning algorithm for any MDPM is bounded above by something of O of let me see, it's like the diameter of the MDPM, which I defined in the notes, times the number of states times squared of 2 times the number of actions, and there's a log t factor here, which I think maybe it's possible to get rid of. But this is the kind of simpler upper bound that one can get.
By polytime, do you mean like as a function of what exactly? Like it converges after polytime steps to the optimal policy, or?
Yeah, I guess depends on how the transitions and rewards are represented, but yeah, I guess I would have to be precise about what I mean here. I'll put it in quotes, but it's basically a fairly efficiently computable algorithm given some kind of representation of the MDP, and depending on what the representation looks like, you might have to be more precise.
Could it be polytime in T, maybe?
Yeah, let's see. So yeah, I mean, so it will depend on the size of the number of states. So I guess it's polytime in the number of states and probably also in the time and the number of actions. I think those are the things that it will depend on. And then maybe, I guess the representation will involve some real numbers for the transition kernel and the value. So yeah, I guess to make this precise, I would have to say something more, but I think roughly speaking, it's a meaningful statement. There was a question asking, can you derive one bandit learning algorithm from its properties? Is the question if you can use a bandit algorithm to get a learning algorithm for MDPs? I'm going to assume that's the question, and the answer is yes, basically. So we could also just take a bandit algorithm whose arms are just policies up to a certain time, and then run that bandit algorithm on the MDP, just trying out different policies, and it will learn. But I think it will be much less efficient than this one because there are the number of policies gets pretty big for if the number of states increases and the number of actions increases. So this is better than just kind of blindly applying a bandit algorithm. Okay, so that's a different question. Let me see what this is. Can you come up with an algorithm to learn bandits by starting from the properties it will satisfy and then not doing any inferential leaps? Like, do you mean given a certain like regret bound, can we like deduce what the algorithm needs to be? If that's a question, yeah. So I would say probably the regret bound is too little information. Yeah, I haven't seen any work in this direction, but it is an interesting question of like how many properties do you need to impose on an algorithm in order to narrow it down enough that you can basically know what the algorithm needs to be. Yeah, yeah. I don't know of any results of that sort, but it's definitely an interesting question.
So do you need?
Sorry, go for it, Alex.
Do you need to know the number of states a priori in order to get this result?
I guess in an MDP, we're kind of assuming the states are the same as observations. So I think we're pretty much implicitly assuming we know the number of them too. So probably yes, it would be the answer.
Is the first theorem proved by something like you keep applying the Bellman update and you prove it must converge using the contraction mapping theorem? Is it something like that?
Yeah, so I was a little vague with this theorem because it also depends on what form of utility you use.
Yep.
If you use a geometric discount, then yes, you can use a contraction. If you're using a average time discount, I think you would have to do a little bit more work maybe. But yeah, I think in spirit, yeah, yes, it is along those lines. Again, and yeah, feel free to go if you need to go, but maybe I'll just state one more theorem, which is a lower bound on MDPs, which says that for all p pi, there exists an m, and I'm being a little loose here for the sake of time, such that the regret of pi with respect to m is bounded below by something of the form square root of the number of actions times the number of states times the diameter over t. So I guess technically this should be for all t and for all a, s, d, there exists an m. And you might have to put some bounds on a, s, and d, and I wrote down the more precise statement in this as well. For example, you almost always assume that there are at least two actions, because if there's only one action, then there's only the optimal policy. There's only one policy, so there's not really anything interesting you can say. And then maybe for POMDPs, I just say they're hard. In particular, even the control problem, so just finding the optimal policy for a known POMDP is in general p-space hard. So there's yeah, just finding optimal policies for POMDPs can be computationally very inefficient. And then the learning for them is also hard because you're not observing the state. So you can end up in a situation where you have a POMDP, which is basically, here's a password that you need to enter, and you only find out that you got the right one if you got the right one. So that way, like, the complexity of figuring out the right password can also be exponentially large in the number of states for the diameter. So for POMDPs, there's no hope for any kind of nice bound like this for MDPs. So they're definitely much harder in their flow generality. All right, so maybe I'll stop here for today, unless there are any last minute questions. All right, and then thank you, everyone.
Thank you,
on
Gergely.
Friday.
Thanks.
Thank you very much.
Thank you.
Thank you.
Bye.
Thank you.
Bye-bye.
Bye.